All right, so for part D, we were looking at this reaction right here, combustion of butane, the last time we looked at the review. And then it tells you that it's an exothermic reaction. And so what we're doing in this question is we are comparing the bond energies of the reactants relative to the products. Basically, the energy is stored in the chemical bonds, and your job is to just basically explain which one is higher, the reactants or the products. So let me give you about a minute or so. I want you guys to first pick. This question is asking you to answer the question, so you got to tell me very clearly, is it reactants that are higher or products that are higher? And then write a quick 1-sentence, 2-sentence explanation for your reasoning. Take about a minute and a half to do that. Again, 2 parts. Write reactants or products, and then justify your answer. Which one has a higher bond energy? Okay, so for part D, you guys should have answered that the reactants have a higher bond energy. And the reason why is because, again, it's exothermic. If it's exothermic, if this is our system, it is releasing energy, right? So it's getting rid of energy from the system, which means that when the reaction takes place, and then afterwards when you have your products left over, the products have lost energy, right? Or the system has lost energy. And so your answer should be reactants, and you would say something along the lines of, in an exothermic reaction, energy is released, and therefore the products are going to have less bond energy than the reactants. That energy needs to go out of the system. So that's the reason why. Okay. All right, let's go to part E. Part E, it says that one of the major sources of air in this experiment comes from the heat that is absorbed in the air. So if we kind of look back at what was happening here, we had the butane lighter, and then you have a fire. And if you've ever been next to a fire, the fire feels hot because the energy goes into the air around it. So not all of the energy is going into the can, and so the energy is lost. Okay, so that's a big source of air in this experiment. But then the question asks, then why is it not a good idea to perform this in a sealed container to prevent energy from leaving? Okay, so I'll just give you the answer just to make a good use of our time. The first thing is when you are running the reaction, the other reactant is oxygen, right? And so if we have a sealed container, what's going to happen is we're first going to use up all of the oxygen. And so you're limiting the reaction with oxygen. So you are limiting the reaction, okay, because you're going to run out of oxygen. So that's one of the reasons. The other reason is the one that's a little bit more intuitive. If you have an exothermic reaction, you are releasing energy, right? And so if you just kind of think about it, if you are putting a little bomb in a sealed container, what is that going to do? It's going to kind of explode. And so what you're going to do is you're going to compromise the integrity of the container. Compromise integrity of the container. Okay, fancy way of saying the container might blow up. Okay, so those are your 2 reasons why. The first is you're limiting the reaction. The second is the container might blow up if you run an exothermic reaction in there. Okay.
And you need both for full credit?
Huh?
You need both for full credit?
No, it doesn't ask for 2 reasons. Just one of those will give you full credit. Yeah, great question. All right, so for number 3, we are going to move on from unit 6 to 7. And so we're going to look at this question right here. I want you guys to try this on your own. It says, even though it's a noble gas, on the right side, the right column, xenon is able to form bonds with other elements. And then they give you a list A, B, C, and D. So this is multiple choice. And you're going to pick which element from this list is xenon most likely to bond with. Okay, so xenon is a noble gas. We said noble gases typically don't bond with other elements, but xenon is able to. Now, which one of these is it most likely to bond with? And then write a short explanation. So take about 2-3 minutes to try this out. You can talk about it with the person next to you, and then we'll go over it. Okay, so in order to answer this, we first need to look at how the elements that are on the list tend to bond with other elements. So if we take a look at lithium, if you guys remember, what type of element is lithium?
Metal.
It's a metal, yeah. And if you have a metal right? How do metals like to bond with other elements? Okay. They like to give electrons, right? If you remember, lithium wants to become Li plus 1, and it does that by giving an electron to another element. Now, if we compare lithium, the valence structure is this, and xenon, which has 8 valence electrons, lithium bonds by giving electrons to another element. Now, do you think lithium is going to be able to give an electron to xenon? No, because xenon has a complete valence shell, so it's not going to be able to, it doesn't want to receive an electron. So the answer for, or part number, can't talk today. Option A is incorrect, okay, because it is a metal. Metals tend to give electrons. Xenon has a complete valence shell, so it does not want to receive an electron from lithium, okay? It's like a creepy person trying to give you a gift. You don't want to take it, okay? All right, let's go to argon now. Argon, if you guys remember, is special because this is also a noble gas. And so argon has a complete valence shell, and xenon also has a complete valence shell. What's that? Yeah, I got those ones. Thank you. Okay, and then xenon, again, has a complete valence shell. Now, if you have two noble gases, both with complete valence shells, are they going to want to react with each other? No, they're kind of loners. They are happy with how they are. They don't want to make connections. Okay, so argon is also incorrect because argon is a noble gas, already doesn't want to form bonds, so why would xenon want to form a bond with it? Okay. All right, our next option is fluorine. Now, if you remember, what type of element is fluorine?
Yeah.
It is a gas at room temperature, but what type of element?
It would receive.
Receive. So lithium was a metal. What's fluorine? Non-metal, yeah. And if you remember, how do non-metals want to form bonds? They either receive from metals, but what do they do with other non-metals? Oof. Yeah, they share electrons. They form covalent bonds. Okay, so we got fluorine, which has 7 valence electrons. Xenon has 8. Okay, and so here we have a possibility because what it could do is fluorine can be like, hey, I'm going to share that one with you, and it's going to want to share an electron. And another thing to remember about fluorine is what makes fluorine special. We talked about this in Unit 7, or no, Unit 8, but there's something very special about fluorine. Oh, goodness. It is the most electronegative element. And if you remember electronegativity, it's how much it wants to hold on to electrons. So fluorine is very greedy. It likes to hold its electrons. And if it sees another element with electrons, it's going to try to take those electrons from it. So your answer is actually going to be fluorine. Okay, and the explanation why is fluorine is the most electronegative element. Okay, so since it is the most electronegative element, it is the most likely to form a bond, or form a covalent bond with xenon. Okay, because even though xenon's a noble gas, it has a complete shell, it's already happy, but fluorine is like a bully that comes and steals its lunch money. It's going to be like, no, we're going to share. These are our electrons. Okay, they're not yours, they're ours. Okay. Carbon would be another option. It is a nonmetal and could share electrons, but carbon is not as electronegative as fluorine. And the question is asking which one is most likely, and so fluorine is just a better answer compared to carbon. Okay, so if you picked carbon, you had the second best answer. So congratulations, but it's fluorine because it is the most electronegative. Okay, so
You're off, Jared.
okay, guys, let's talk about number 4. So let's talk about O3 minus. So if we take a look at regular oxygen, I'm just going to draw the full structure for us. It's going to be 2 shells. Okay, and then you're going to have 2 in the first shell, and then 6 in the valence shell. Okay, total of 8. Everybody good with that?
Yeah.
Okay, now let's talk about O3 minus. To become O3 minus, you need to lose 3 electrons. Okay, so let's take a look at which electrons we're going to lose. So we have to take away from the valence shell. So we got to get rid of 1, 2, and 3. Okay, so we're not breaking the valence shell like before, but we're going to talk about why you can't lose 3 electrons. So in order to do this, we can't just look at the shell model. We actually need to look at the electron configuration chart. Okay, so if we take a look at the electron configuration chart for oxygen, we start at 1s, we look at 2s, and then we have 2p. Okay, everybody tracking? Okay, so oxygen has 8, so let's draw our electrons on the electron configuration chart. It's 1, 2, 3, 4, 5, 6, 7, and 8. Okay. All right, so we have our electron configuration chart. Your question? Oh, I'm so sorry. I'm tripping out. Yes, it's not lose, it's gain. I am actually tripping. You gain 3 electrons. What am I talking about?
Wait, oh my god, I was like losing my
Yeah, I'm like losing my mind right now. Sorry. You're gaining 3 electrons. My fault. What am I even doing? Okay, rewind. Okay, gain 3 electrons. Sorry guys if I messed you up. So if you gain 3 electrons, you gain 2 in the valence shell first, right? And if you gain 2, what's special about O2 minus?
That it reaches same amount of electron as a noble gas.
Yeah, it has its noble gas configuration, right? So it has a complete valence shell. Okay, so complete valence shell. Okay, now oxygen is happy now, and so to become O3 minus, what does it need to do? It needs to gain a 3rd shell. Okay, and so this is unlikely, and this is the reason why, is because O2 minus has a complete valence shell. It's in its noble gas configuration. The energy level is stable. In order to get the 3rd electron, what you're going to be doing is you're going to be creating an unstable energy level. Okay, and that's the reason why. Sorry about that earlier, guys. It's too early for this. Okay, and so yeah, it's because O2 minus, complete valence shell, gaining the 3rd one would create a 3rd shell, which is an unstable energy level. Let's also talk about where I was going with when I was tripping out. Okay, so let's talk about O3 plus. Okay, so the electron configuration, if we take a look at this, 2, 3. Okay, we have 8 valence electrons. Okay. Okay, everybody go to the electron configuration?
Yeah.
Okay, now, for where I was going, is we have to look at this right here, okay, the 2p subshell. Now, if you look at the 2p subshell, you guys see how we always fill in the subshell by putting them in separate lines, and then we pair them up afterwards, right?
Mm-hmm.
Now, what happens is when you pair up an electron, it's easy to get rid of the electron that's paired up with another one, okay? Because if you remember, electrons repel each other, right? So taking away the first electron, not too much ionization energy, okay? So O plus is relatively easy to make. However, O2 plus is very difficult to make because what you're going to have to do is you're going to have to take away this electron right here, which is already by itself in this line. And so there is no repulsion to make this easy to take out. And so O2 plus is very difficult to make because what you're going to have to do is you're going to make this subshell unstable by getting rid of one of the electrons in the lines. And so that's where I was going with that. Okay, so just keep that in mind. It's a lot easier to split up paired electrons in the subshell than it is to break up or to remove an electron from one of the lines when it's by itself. Okay, that's where I was going with that. So yeah, O2 plus is difficult, and O3 plus will be even more difficult to form. All right, guys, another minute, and then we'll go over it together. My trip balls. I hate them all too.
Unit 6 is plug and chug.
Alright guys, let's go over 5. So part A is asking what's the highest subshell that electrons occupy in this element. So we're going to look at the peaks. This peak is 1s, 2s, 2p, 3s, 3p. So your answer will be 3p. Okay. Any questions on that one? Okay, not too bad. Alright, next we have to identify the element that is represented in this diagram. So we fill in the inner shells before we get to the outer shells. So this will be 1s2, 2s2, 2p6, 3s2. And if you look at 3p, it's about half the height of 3s, right? So it'll be 3p1. You go to your periodic table, and it is aluminum. Okay, and if you're Australian, it's aluminium.
Oh yeah.
Those crazy Aussies adding syllables. Okay. Are you Australian?
Yeah.
Oh. Y'all crazy.
Oh, okay.
Where is the aluminium? Alright. Anyway.
Normal Australian.
Normal Australian. Got it. Aluminum. Alright. So, which ion charge would be most likely not possible with this element? And explain why. So, we're going to look at what's not possible. So, if you think about aluminum, what is the ion that aluminum wants to form? +3. Good. Okay, it wants to lose the third. So which one is the most unlikely? It's going to be aluminum +4 because you're going to be breaking up that happy valence shell. Okay, so once you get to aluminum 3+, it's going to have a complete valence shell, and so it's going to be very difficult to break up the aluminum +3's complete valence shell. Taking away that one will be +4, and that's the reason why. You're going to be breaking a complete valence shell. Okay? Any questions on 5? Hopefully not too bad. There will be PS questions on your exam, so just make sure you're familiar with solving them. Okay? Alright, so for this one, I didn't tell you guys, but this is a calorimetry question. So we're going to have to use that the set of equations that we talked about. The Q of the metal, negative Q of the metal is going to be equal the heat of the water. Okay? And the reason why is it kind of tells you in the question, it tells you that you have a test tube with your metal, right? And then you heat it up. And then you put the, hold up, there's going to be water in there. Okay, and so you heat up the metal in the boiling water. You put it in the calorimeter, right? And then what's going to happen is the metal is going to release energy into the water, and it's going to go up to a certain temperature. Okay, and the question is asking you to find the maximum temperature of the water. So let's go through the different variables that are in the question, and then after that we will see what variable we're looking for. So if you expand the Q equations, the heat equation, it's going to be MCAT, right? So on the left side, we're going to put, and if you flip the sides, that's totally fine. It's going to solve the same way. But it's going to be negative mass of the metal, specific heat of the metal, delta T of the metal. And then on the right side, you're going to have the mass of the water, the C of the water, and the delta T of the water. Okay? And so let's plug in the values that we have. So first, insulated container is used to hold 47.6 grams of water. And so the mass of the water is going to be 47.6 grams. Okay, so far so good? Okay, I'll kind of list them out right here on the side. The mass of the water is going to equal 47.6 grams. And then it tells you that the water is at 35 degrees Celsius. So the initial temperature of the water is going to be 35 degrees Celsius. And then it says a sample of copper weighing 18 grams. So the mass of your metal is going to be equal to 18 grams. And then it says you heat it up in a boiling water bath at 100 degrees Celsius. If you heat something at a certain temperature, eventually it gets to that temperature. So the initial temperature of your metal is going to be 100 degrees Celsius. Okay, and then you move the copper into the water in the insulated container. It says the specific heat of copper, so the C of the metal is 0.385 joules per gram Celsius. And then the question is asking, what is the maximum temperature of the water after the copper metal is added? So, anyone want to take a shot at it? What is the variable you're looking for at the very end? Not C of the metal. You have C metal right here. It's T of the water, but specifically T what? Yeah, T after or T final, TF of the water. Okay, so the question is asking you to find TF of the water. All right, any questions on the setup, the variables, the numbers that we got? Everybody good with that? Okay. So from here, it's plug and chug, and then it's just a bunch of algebra. And so let's plug in our values, and then we'll see what we get. So let's start from the left. So negative mass of the metal, so it's going to be negative 18 grams. C is going to be 0.385 joules gram Celsius. We can expand delta T into TF minus TI, right? So it's going to be TF minus the initial temperature of the metal, which was 100 degrees Celsius. Okay, equals, and then we're going to plug in our values for the water side. Okay, I'm going to rewrite this equation just so it's kind of the equal sign lines up, but I'll give you guys about 30 seconds or so. See if you guys can plug in the values correctly for the water side. God bless you.
We don't need to make a count. We don't need to make a count.
All right, everybody good with what we got up there? Mass of the water 47.6. Not calcium. The specific heat of the water is 4.18, and then the TF minus 35 degrees Celsius. Okay. Now, a key thing that you should notice as you're solving this problem is that the TF is going to be the same for the metal and the water, right? Because as the metal releases energy into the water, eventually they will end up at the same temperature. The metal temperature will come down from 100, water will go up to 35, and they'll meet in the middle, thermal equilibrium. Okay, so this actually makes the algebra a little bit tricky for some students because you're solving for like variables that are split apart, so you need to combine them before you solve for it. But let me give you guys a chance to do that. See if you guys can do the algebra for this, and see if you guys can find the final temperature. Now, keep in mind, the final temperature, if you get your number, it has to be between 100 and 35, right? Because the metal is coming down from 100, and the water is going up from 35. So they should meet in the middle somewhere. So if you get a number that is not between 100 and 35, you automatically know you messed up on your calculation somewhere. Okay, so go ahead, try that out. A little algebra practice, and then we'll go over it in about a minute and a half or so. Okay, so let's start with the left side of the equation. So first thing we're going to do is 18 times 0.385. Okay, so you should get 6.93. So on the left side, you should get negative 6.93, and then TF minus, and I'm going to drop the degrees Celsius because the answer is going to be in Celsius. Okay? All right, so good with the left side? Okay, right side, we're going to do 47.6 times 4.18, and that's going to give us 198.97. Okay, and then we still have our TF minus 35. Okay. Everybody good? All right. Now what we need to do is we need to do some algebra shenanigans. We need to distribute on both sides. So you're going to do 6.93 times negative 6.93 times TF. So it'll be negative 6.93 TF. And then plus, because the negative is going to cancel out with the minus, so times 100. So it's going to be plus 693. So that's what we get on the left side. Negative 6.93 TF plus 693. Okay. And then on the right side, we're going to distribute as well. 198.97 TF, this time minus because of the negative sign. And we're going to do 198.97 times 35. And that should give you 6963.95. Okay. All right, so far so good with the algebra. Okay, we just distribute. And then what we need to do is we need to separate, or we basically need to solve for like terms at this point. So what we're going to do is we're going to move let's move negative 6.93 TF to the other side. Now to get rid of this, we just need to add by 6.93 on both sides. So on the right side, we'll get 198.97 plus 6.93. And so on the right side of our equation, we're going to end up with 205.9 TF. And that's if we add these two values together. Okay? And then to get the numbers without the variables together, we're going to take 693 plus 6963.95. And on the left side, you should end up with 7656.95. Okay. And then from there, very easy to solve. You just need to divide by 205.9 on both sides, and you should get an answer of 37 degrees Celsius. Okay, and if you look at our answer, it makes sense with the scientific principle, right? The metal cools down, the water heats up, and they meet in the middle, albeit very close to the water, which makes sense, right? Because if you remember, water takes a lot of energy to heat up. Metal has a very low specific heat, so it contains less thermal energy. All right, guys, I have the answer up there for you. Pretty simple thermochem stoic. You start with 558 kilojoules of energy. You just use the relationship in the equation, 180.6 per 2 moles of NO. Molar mass of NO is 30, and then you just multiply it out, 185.38 grams. All right, guys, let's go over number 8, and then we'll take our break. So we have our overall equation up here. So we just want to rearrange the 3 steps in order to get, what the question is asking us to solve for. So first thing we need to get is 2 carbons on the left side of the equation. So we're going to look at reaction 2, and it already has that. But we just need to double the reaction to get 2 carbons. So we double reaction 2. Okay, so just make sure you multiply the enthalpy by 2. All right, next thing we need is, let's go to the C2H5. If you take a look at C2H5, it's on the product side. And so if we look, we have C2H2 on the reactant side of equation 1. So we got to flip it. And if we flip it, we just need to multiply by -1. Okay, just change the sign. So if we do that, the 2 carbon dioxides are going to cancel each other out. And if you look, there's 2 oxygens here, 5 over 2 oxygens here, 2 is 4 over 2. And so this gets us down to 1/2 oxygen on the product side. And then last but not least, we just plug in equation 3 exactly the way it is. The H2Os will cancel each other out, and the half oxygens will cancel each other out. And then the overall reaction on the reactant side is 2 carbons plus H2 produces C2H2. And then you just sum up the enthalpies, and you should get 226.7 kilojoules. Alrighty, guys, so I got the answer for you up there. Delta H is products minus reactants. So just plug and chug. Just make sure you multiply by the oh my god, I can't talk. By the coefficients in the chemical reaction. And just make sure that you're aware of this, but when we have combustion, it is an exothermic reaction pretty much all the time. So your answer should line up with that, and so it is an exothermic reaction.
I thought